Hi, this is Andy. This is the first real video, I guess, of my channel, and it's going to be on a buck regulator. I've been given this circuit to review, and I've also been asked for some layout guidance on this circuit. So let's get into it. So first things first, what is the chip? It's a TPS57140, as it says up there. It's a DC to DC converter, current mode control. It's got a few pulse skips, eco modes. It's configured at the moment to have 18 volts in, although it can take up to 42 volts. It's configured to push a 1.2 volt out. I guess it's going to go into some sort of core FPGA or microcontroller. So let's have a little bit of a quick peek. It's got some MLCCs here. Resisted divider here for the enable. Straight off, I would have said divide those values by a factor of 10. I personally like to have a bit more of a stiffer current going through. Some of the boards that I design, or some of the boards that I've designed that go into systems that are excessively noisy, and having a bit more current flowing through there gives you a bit of board tolerance, to be fair. So that's one thing I would do. It's got a standard catch diode inductor, standard TMPW resistors for precision. Those are our voltage setting resistors. TANTs. These are poly TANTs, so yes, airframes tend to accept poly TANTs, but I'd have probably gone with an MLCC version, to be fair. That's just my preference. R2. Now, people tend to put 0-ohm links for a variety of reasons. One, they're a bit unsure of the circuit. It's going to do the right thing, so they'll pop this. They'll put a load across C5 and make sure the circuit behaves itself before putting the link back in. That way you don't destroy anything downwind of this 1.2 volts. The other reason is maybe somebody wants to profile the current, so they'll pop this, put a little bit of copper ring across that, and then put a current clamp on there. So that's another reason. But either way, I wouldn't have used an 0805. I'd have probably used an RCL 1218. And the reason for that is it's got a slightly reverse. An 0805 is got like small pads, big body, whereas an RCL, a 1218, has got big pad and a tiny body. And the reason for that is, let me just quickly draw this. So what I mean by is like that. That would be what an RCL 1218 would be, and this would be sort of an 0805. So you can see that the one above, we get a much lower impedance coming off it, and it helps in power delivery. So that's one of the reasons I would have done that. But it's not my circuit, so I'm going to go with what I've got. Okay, so we'll save this and we'll add a new to project PCB. Just click save. Right, save there, and then we'll go design, import, valid, execute. Of course, I've got the libraries all set up. The design was given to me in PDF form. I recreated it in Altium. I'm more familiar with Altium. I've been using it for well over a few decades. Actually, when I first started using it, it was Protel 99 SE. Actually, it might have been Protel 98, actually, but maybe. Yes, I think 99 second edition came out after that. Yeah. So that's a long time ago. So what I'm gonna do is, first of all, because I hate the size of the designators, I'm gonna select all the designators. So text height, width, they're all the same, and designator same. Right. Okay. So as you can see, all my designators are now selected. When I go to my properties over here, I'm going to go 15, 3. So 15 height, 3 stroke width. Excuse me. And you're probably going, oh no, Andy, you can't make that. They won't be able to print that on the silk screen. Not to worry. I tend to hide all my designators anyway. I tend to do a lot of very dense boards. You haven't got room for designators. So what I tend to do is what I'm about to do now is I'll pull all the designators into the center of the pads of each part like this. And what I'm going to do is I'm going to pause and then I'll come back when I've done it. Okay, so that's all that done. The next thing I'm going to do is I'm going to go to my mechanicals. I'm going to again filter on that, anything mechanical, 16, choose those, click OK, and I'm going to say again 15, bold. Let's zoom in and have a look. It's probably too small. Yeah, we'll say 25. That's about right. Okay, cool. So what I'm going to do, I'm also going to pull these into the centers, nothing more at the moment, and I'm going to pause it and I'm going to bring you back when I've done all that. Okay, so I've done all that. As you can see, they're in the centers. I tend to do that. That's the first thing I do. Pull my components in, either a sheet at a time or all together, because Altium's pretty good at organisation in terms of pulling stuff in. And then I'll put all my designators into the centre. Like I say, I tend to not to have them on the silk screen. I tend to put other more pertinent information on the board, like debug information and so forth. The reason I went for 15.3s is because that's a good value for 0402s, and the smallest part on here is an 0402. So that's why I'm doing that. So the next thing I'm going to do, as you can see, we've got this here, which is failing DRC. That's what that colour means. So I'm going to go into my rules, so I haven't set it up yet. I'm going to set the clearance to 6. So hit apply. My width, at the moment I'm just going to go with 100. Apply. Routing bias. Now I'm going to use 2412s wires on this design. The reason is in aerospace we tend to use boards thicker than 2.4 mil. 2.4 millimeters is like the minimum, really. So there you go, there's DRC gone. So that's why I've used that. And the reason for 2412s while I'm here on 2.4 mil is that when you work out the aspect ratio of the drill to the board distance, thickness, you get about an 8:1 aspect ratio, and we try and keep it below 10 to keep the reliability up. And that's really the only reason at the moment for that. So just to keep the reliability high. Okay, so now what I'm going to do is I'm going to start to place this out. Now when you start placing a buck converter out, you need to take a few things to note. What can I say? There are certain parts of the buck regulator which need higher priority in terms of layout. Let's put it that way. Okay, so I'm going to go back to the schematic. Right, so power delivery into the buck regulator is important. So we've got P18, that's part of your PDN network. C1 and C2. Forget R1 and R3, that's just an enable, so they disappear more or less. So you want to try and get C1, C2 and your V into pin 2 and the ground, a nice tight loop. Okay, that's one aspect. Now delivery out the buck is also very important. So the pH is the output. So D1, L1 and C4 and C5, and obviously in this case R2, also need to be placed with a level of care. The other bits which come down is the compensation network. That needs to be quite tidy, and the rest not too bad. So that's what we'll do. We'll focus on that. So the first thing I'm going to do is I'm going to look at D1, L1 and the two output caps. Okay, so we'll grab the part. First I'm going to change my grid to 5. I'm going to grab the part in pin 10 and move it around a little bit and drop it. Now I know that the center of that pin is on the grid. Okay, and that's the only reason I've done that. Okay, so now we grab the catch diode and we can center that up. I'm going to pull it out the way because between these two pins here, which I'm highlighting, there's a cap. Okay, so I'm not sure at the moment whether I want to continue this ground through at the moment or I can get away with putting the cap there. We'll have a look. So I'm going to leave it spaced out. The next thing we want to put in is the inductor, which is this. So we get that quite close. Click on that output node. Caps, so C4. We'll leave that there. C5. Okay, and the last one in the loop is R2. Okay. Brilliant. So there's some parts on here, the compensation networks. Now when I've worked out how much room I need around here and the resistive divider, so they are on this side as well, then I'll be able to pull these in and condense the network. So the next part is the P18V node, and we've got C2 and C1. So what I'm going to do is I'm going to rotate that. I could put it there, but I'm not. I'm going to move it up a little bit. I'm going to place it about there, and I'll tell you the reason why in a bit. Okay. Brilliant. Okay, so the reason why is that I want to put a polygon on P18 because I don't want to use a track. So I want to be able to come across. So essentially underneath this pin here, underneath this pin, straight across, big thick track around on a polygon, and I'll show you what I mean in a bit. So I'm going to pause the video and place all the bits and then bring you back. Okay, so I've done a quick layout placement. This is where I've got, so I'll just take you through it. So P18V, so we got power in and then ground, which is quite tight. The output is going to go through here, through the inductor. That's going to get studied down with some wires, and then we've got the output, and then we're going to wrap this back through here. Resistive voltage divider there, and then the compensation network is here, which is quite tidy. This is the setting resistor for frequency. This is the open drain value, and this is the voltage set, so the enable setting. So that's where we are. So what I'm going to do now is I'm going to show you how I would essentially track this now. But the first thing what I would do is I draw polyplanes. So I want to make this part, this node which I'm highlighting, very, very low impedance. So we're going to go to a 1/3 grid. I'm going to place a solid region, and we're going to pull this across like this. Now you see how this is coming off 45 degrees there. If you press shift and space, you get various different options. So I'm going to try and make them even. 1, 2, 3, 4, 5. Here we go. Not too close. 1, 2, 3, 4, 5. There we go. Okay, cool. Brilliant. Okay. Let me change that now to 1. Okay. Let me save. So that's quite a fat polygon there. We haven't finished with this yet. We're now going to place another one, another solid region here, and then we're going to come down. Make sure we've got enough some wires. So 1, 2, 3, 4, 5. We can incorporate that if we wanted to. May as well. 1, 2, 3, 4, 5. There we go. Brilliant. So now we're going to select both of these. We're going to right click, polygon actions, combine. Okay, so that's combined, that's polygon into one. Okay, so you can see now that the 18 volts, if I click on that node, it's got a very, very good connection into that pin. Okay, we'll do some quick routing for the rest. Okay, bring that to there. This will come up. Like that. This can now essentially come down. We'll come into that. Right, that's what we want. This will go the other way, make it easier on myself. And then this we can bring down. There you go. Brilliant. So, I mean, that was pretty quick. And some people will go, oh, we'll just connect that to that, that to that, that to that, that to that. You know, and I have seen designs like this, and they, rightly or wrongly, people think that that's acceptable. It is rooted, but it's not very good in terms of keeping a very low PDM and optimizing the function. Now you've gone to some trouble laying it out. Okay, so what I'm going to do is I'm going to pause. I'm going to put all the polygons in because I'm conscious of the video being so long, and then I'll bring you back. So I'm back. I've added a few polygons in, and I've seeded a few wires. So let's just take you through. Let me just root this. Okay, so our output here goes through L1, sorry, D1, L1, C4, C5, and then out through R2. So this is our output here. Goes to D1 there. If I show you, there's the diode here. Goes straight into the inductor. Then it goes straight out, and that's our output here. I'll put a polygon connecting the other side of the inductor to the caps. So that gives me a very low impedance there. My voltage pickoff point is here, and then it's returned back here. My compensation network, it is quite tight. Still need to see some wires there. My soft start cap is here. It's quite tight. Timing section and enable. So everything is quite tight. So from an 18 volts point of view, comes in, goes through the chip, and you've got a very, very tight ground here. I've decided not to carry this part of the plane through because I'm going to pull it, I'm going to carry it down, and this has got a good connection because this will be a multi-layer board, so the power plane under there will connect it. So we'll just now start to finish this design off. So we want a that will do, and we'll duplicate that. We'll pop that there, that'll be fine. Good, 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 good. And our open drain output, there you go. So that's pretty cool. Okay, I'm just going to get, I'm going to connect all these up. So I'm going to go to my layer stat manager. I'm just going to add 2 extra planes. Just go to the presets and add a 4 in, and hit save, and come back, and then I can tell this that this is 0 now, and they're all connected. Now, you notice how big these are? You see how they start interfering with each other? You go to design rules. You don't need them that big. Plane connect. So you go, it's 20. I normally have a 10 or an 8. Hit apply there. And then here I have a 10. And then here we're good. We're okay now. And they should all shrink down a little bit. There you go. Brilliant. So we've still got a little bit of interference there, but that's not too bad. Now I'm going to draw the last polygon. So place a solid region. What I'm going to do is I'm going to come from here, and I'm going to go around, come around here. I'm not going to incorporate. I could incorporate that, I suppose. Yeah, why not? I'm just doing it fairly rough now, just so get the video done, but you'll get the gist of what I'm trying to do. And then, I mean, I could go all the way around really, and why not? Actually, let's just do that. So we're going to go up, and I'm going to do that, which is all right. That covers everything else. I'm going to go up to here. And then just make that level. Okay. So now this power pad now has got a big polygon connected to it, and I'm going to put wires throughout this part here to give a good low impedance down to ground. A lot of people sort of go, oh, you put polygons everywhere and you haven't thermal relief them. I've been doing solid regions for more than 2 decades now. Various different types of parts, 0402s, little sods, and diodes, and various different things. I've had no tombstone in, no issues. As long as the profile is correct on the preheat on the board, proper paste, mass geometries, it should all be okay. And I've had no issues. I mean, I make a lot of boards in my own lab area, and I've had no issues with tombstones. I've also gone back to the CEM, the contract electronics manufacturer, and asked them, have they had any issues? Do we need to change any geometries? How can I help? and nothing. They've been happy with what they've been given. So so yeah, using solid polygons to get low impedance solutions, especially on power supplies and so forth, I think is only a good thing, to be honest, personally. So what I'm going to do, I'm going to just pause the recording, put some thermal visors in, and bring you back. Okay, so we're back, and there you go. In reality, it probably took an extra 10 minutes. I just didn't want it to go over the 30-minute mark, to be fair. So let's look at it in 3D mode. There you go. Lots of... Actually, let's just, while we're here, let's change to 10. Let's go and press tab. Yeah, that's 10. And what I'm going to do, I'm just going to draw a board outline. I'm just going to draw a simple board outline. Nothing special, really. Just to give it a shape. Shift S, single layer mode, design, board shape, from selected objects, brilliant. There we go. Shift S. Now when we look, we've got a board. There we go. So that's not too bad. Let's have a look at some of the copper regions before time runs out. So input. Got a very good input. Nice tight nice tight out control current loop coming right back round. I've got hiccups, sorry. The output, there you go, comes through there, comes in there and returns back in. Oh dear. So there you go. Not too bad. This is probably how I probably could condense it a bit more, but I don't think it's a bad layout. Let's do a 3D, and I'll take you through the clear filter. So there's the top. Okay. There's the copper regions. You can see how the copper regions forming underneath the part. It's got lots of thermal wires there. The power plane, those two are very good connection. Like I said, this is the V-in caps and the output caps, and we've got a good solid power plane underneath. I haven't done anything with that power plane and bottom layer. So let's go back to 2-layer mode. Change that to 0 volts. Okay, and now we'll do a 3D load, and you'll see now that both the ground and the power are connected to 0 volts, and lots of thermal cramping there. So there you go. This is how I would have routed TPS57140. Hopefully it's been some educational, and hope you enjoyed it. Okay, cheers.